Hello, everyone. Welcome to the series Mud Talks, Artificial Intelligence Powering Human Exploration of the Moon and Mars with Jeremy Frank from Pomona College class of 90. My name is Vanessa Chu, Assistant Director in the Office of Alumni and Parent Relations. We thank you for attending today's event and we hope you and your family are well. This talk is being recorded and will be distributed after the event. Please feel free to type your questions in the Q&A box, not the chat, and we will try to get through as many questions as we can. Now, to briefly introduce our speaker, Jeremy majored in mathematics during his time at Pomona College and received his PhD from the Department of Computer Science at UC Davis. His work involves the development of automated planning and scheduling systems for use in space mission operations, the integration of technologies for planning, plan execution, and fault detection for space applications, and the development of technology to enable astronauts to autonomously operate spacecraft. Now, I'm going to turn it over to our speaker. Jeremy, take it away.
Thanks very much. Let me go ahead and share my presentation here. All right, how is that? Is everybody able to see that? Yes, great. Okay. So, without further ado, let's just go ahead and get started. So my plan for this talk, I'm going to talk for perhaps 30 minutes, maybe a little bit longer, and that ought to leave plenty of time at the very end for questions. And I know that there are going to be some great questions, and I'm looking forward to that. So without further ado, artificial intelligence powering human spaceflight exploration of the moon and Mars. So let's start off with a little bit of motivation. So this is a picture of Phobos. Phobos is one of the two moons of Mars. This picture was taken by the Mars Reconnaissance Orbiter in about 2008. And you know, pictures of distant places that are taken by spacecraft are motivation enough for anybody, so it seems. But as a little bit of additional incentive, imagine, if you will, that there is a spacecraft that is in orbit near Mars, perhaps near the moon of Phobos, and that this spacecraft has people on it. And this is the first human exploration of Mars ever. And so what better motivation than that to think about AI as powering human exploration of the solar system. Now, what I'd really like to do is I'd love to tell you that that is what the plan is and that humans are in fact going to Mars in the not too distant future. But alas, I can't do that. I have something almost as good to talk about, and I have some more information about this that I'll share a little bit later. NASA and a number of other nations are engaged in what is called Project Artemis. Project Artemis's purpose is to send humans back to the moon for the first time since the mid-1970s during the Apollo program. And what I have here is a graphic that shows a couple of things that are happening right now as part of the Artemis program. So across the top, we see a series of space missions with astronauts on them eventually. The first of these, Artemis 1.
Jeremy?
Yes.
Sorry to interrupt. Your presentation is not moving on to the next slide.
Really? Well, that's interesting. All right. Let's see. Let me go ahead and escape out of that. What are people seeing now? Are you seeing anything?
Is it
just stuck on the first slide?
Nope, I see your third slide now. And it's not in presentation mode.
So I just got out of presentation mode and you only see the first slide?
We see the third slide, but it's just showing all your slides on the side as well.
Oh dear. Well, maybe we're going to have to do this not in presentation mode in order to make this all work out. Why don't we just do that? So I'll just hide the side, and sorry for the extra white space. We'll try and hide as much of that as we can. All right. So you're still seeing the third slide, the Artemis overview slide?
Yes.
All righty. Well, so let me go back and let me do Phobos again. So, all right. So we missed all of that. Okay. So here's Phobos. Now imagine that we have this human occupied spacecraft near the moon. The animations aren't going to come through on this slide, but that's all right. There are no other animations in the talk, so good deal. Okay. So let's talk about Artemis. So as I said, the purpose of the Artemis program is to send humans back to the moon. So across the top, the first couple of things that we see here are the NASA's first human rateable spacecraft since the Apollo spacecraft. This vehicle is called Orion. Orion is going to have its first mission very soon. It's called Artemis 1. It will be an uncrewed lunar mission, and it's going to have an Apollo 8 style trajectory. So the vehicle is going to launch, it's going to go to the moon, do a couple of orbits around the moon, and then it's going to return. After that, we will have Artemis 2, which will be the first human return to the moon since Apollo. This will be followed by what's called Gateway. And on the far right top here, we see Gateway. Gateway is a space station that will support crew. It will be in an orbit near the moon. It's a complex orbit, and it will provide humans access to go to the lunar surface relatively easily. Across the bottom, we see a number of surface missions of various different types. There'll be a variety of lander missions. This is being managed by something called the Commercial Lunar Payload Services Program, or CLPS. This is a commercial program that's designed to deliver payloads to the moon. There will be some rover missions. There's a NASA rover mission called Viper, which is designed to look for water. And ultimately, there will be surface habitats where the crew can go and live and work. They will have vehicles that they can drive around in. And what distinguishes this return of people to the moon from when we did this in Apollo is that we're going to stay for much longer periods of time. Previously, we only had crew on the surface for a few hours, small digit numbers of hours. This time, the crew will be there to stay for much longer. So we won't be going to Mars just yet, but being able to go to the moon and live and work on the moon for extended periods is preparation for going to Mars eventually. So with that additional motivation, let's talk a little bit about the rest of today's talk. So what I'm going to do for the next little while is I'm going to talk about mission operations, and in particular, human spaceflight mission operations. We'll talk about what happens in mission control as missions are being operated by flight controllers. And we will then ask ourselves, okay, so if this is what people are doing, why do we need to talk about this? Well, they won't be able to do this for the future missions. And that will set the stage for some AI technology that will be needed in order to serve the function that's being served in mission control. For the next part of the talk, I'll go over a couple of different subfields of AI that are important for use in performing those mission operations functions: planning, plan execution, and fault management. And these are supported by a host of associated technologies that we'll also talk about briefly. And I expect some people are wondering why machine learning is not on my list, and we will talk about machine learning, don't fear. At the very end, I'll go over some technology development projects that we have been doing within NASA in order to develop and demonstrate these AI technologies both in space and also in high fidelity test environments. And that should bring us to roughly the 35, 40-minute mark, and that'll leave plenty of time for questions at the end. Okay. So first and foremost, let's talk about mission operations and human spaceflight mission operations from the perspective of exploration to these destinations, whether it be Moon or Mars. So this is an image of mission control at Johnson Space Center. This is one of several mission control rooms within what is now called the Chris Kraft Mission Control Center. This is where space missions like the International Space Station, soon to be Orion, are operated. And you see that there are quite a lot of people in here, and they have a lot of different jobs. And so the first thing that we need to do is ask, so what is mission control? What do these people do? So previously, the Apollo era vehicles and Mercury and Gemini before them, they were flown by the astronauts. And the astronauts more or less were in charge, and mission control was there to help them out. But slowly but surely, the astronauts on board the International Space Station, they don't fly the International Space Station in any meaningful way. They don't really operate it. Their purpose is mostly to do science. As you'll see a little bit later, they have some other things that they have to take care of. But mission control is the power company. They're the plumbers. They're the air conditioner repairmen. They're the geek squad, the phone company. Pretty much, if something on board the International Space Station in particular needs to be taken care of, it's mission control that does that job. And in order to do that, we have to have communication with the vehicle in as close to real time with as little light time delay as we possibly can. And when we go further away from Earth, that becomes more and more difficult. So we'll talk a little bit about light time delay in a bit, but it's about 1.2 light seconds delay to Earth-Moon Lagrange 2. It's more like 1.5 to Earth-Moon Lagrange 2. It's 1.2 to the surface of the moon. It's more like 2.5 minutes to Mars when Mars and the Earth are as close as they can be to each other. And it's more like 22.5 when Mars and the Earth are as far away from each other as they possibly can be on opposite sides of the sun. So having all of these functions for your human spaceflight mission of the future located on Earth simply is not going to be tenable in the future. And so that's really part of the motivation. And so let's talk for a bit about the major functions that each of these flight controllers are doing as they're sitting here in mission control. So the first of these functions is monitoring. And the purpose of monitoring is for flight controllers to understand what is the state of the spacecraft. So our spacecraft are equipped with a number of different sensors, many sensors. They are sensing just about everything you can imagine, everything from temperatures, pressures, voltages, currents, flow rates of gases, flow rates of fluids, the positions of various switches, the positions of various valves. All of that information needs to be conveyed to flight controllers so that they know what's going on with the state of the with their part of the vehicle. And so once we get the bits down to Earth, we have to assemble those bits into engineering units, pressures, temperatures, voltages, and so on. And in order to make this all sensible to people, we have to group them both into physical and logical displays. And these displays are both specific to major spacecraft systems that are the care and feeding of a particular person. And they can also be particular to a particular phase of the mission. So if I'm the power systems flight controller, I don't necessarily need to know what the crew's heartbeat is, right? So this is part of the job, is to say who needs to know what piece of information. But if I'm a power systems flight controller and it's a normal day, the crew's just busy doing their science. We're not relocating the vehicle by firing thrusters. We don't have crew outside doing an extravehicular activity to sew some solar panels back together. And yes, that did happen. If it's a normal day, then I need one subset of information from the power system. But if I have, say, a vehicle docking, then perhaps I need a very different set of information, or I want the information organized a different way. And so that's this process of trying to figure out how to group my information into displays. And the purpose of all of this, as we said, is so the flight controllers can monitor the state of plans, make sure that everything is going the way that it's supposed to go, and make sure that they have what's called situational awareness and know the state of the spacecraft. So the next major function we'll talk about is planning and scheduling. So the purpose of planning and scheduling is to figure out what the spacecraft is supposed to do and when. Those plans and schedules are created in order to achieve specific objectives. So if the objectives, say, of crew planning, planning the astronaut's day, is to maximize the amount of science that they're going to get done, then that's the responsibility of one set of people, is to build that plan. On the other hand, if I'm a power systems flight controller and I have to plan a docking maneuver, I've got to point the solar arrays in directions that don't maximize power generation. So that's a different planning problem, and it's a different planning goal. And furthermore, these plans are created for major spacecraft systems by separate teams of people, and then all they have to do then they all have to get together and integrate all of their disparate plans into a single plan and make sure that everything is internally consistent. And if it's not, or rather when it's not, then they have to go back to the drawing board and say, whoops, well, we didn't do that right, and we have to do this again. So when we think about what happens sort of the day of execution, this set of plans was created roughly 2 weeks ago for the International Space Station. So everything that's happening on board Space Station today was planned and sort of set in stone 2 weeks ago. But the unexpected does happen, and when that happens, you may have to change your mind and decide what to do on much shorter timescales. They don't like to do that, but we all know it happens. How are we doing on the slides? Everything looking all right?
Looking good.
All right, good. Okay, so the next major function we'll talk about is plan execution. So building a plan isn't much good unless you actually do what you said you were going to do, and that's what execution is all about. And so when we think about our robotic spacecraft, these are spacecraft that have electronic command and data interfaces, and so I can send a command over that interface and expect the spacecraft to do something. The crew do not have electronic command interfaces, so they execute plans a little differently, but it's more or less the same. It's the same issue. We need to make sure that the plans are actually being performed the way that we expect. And in the event something is going wrong, then we may need to deal with replanning. We have to monitor them, see the previous slide on monitoring. Or we may have a problem. And now it's Apollo 13 time, and we have to talk about faults and fault management, which is our last function. So with respect to fault management, the first and foremost question that people ask is something wrong in the first place? How do we know that there is in fact a problem? And the second thing that we have to be concerned about is that if there is a problem, what are the impacts of the problem that we have experienced? So it may seem like fault management is just sort of a subset of monitoring, but it's more than that, as we'll see, because partly if there's a problem, we may need to do some work in order to figure out what the real problem is. And then there's this consequence assessment function. And the way that I like to talk about fault or consequence assessment is as follows. So suppose that the fault that I have experienced is that I have lost a light bulb. So a light bulb on my spacecraft has burned out or is not lit when I expect it to be lit. So this is clearly a fault. I expect the light to be lit. It's not lit. However, whatever the reason for this light not being on, it may not be a very consequential fault. If the only thing that it's done is dim the cabin a little bit, perhaps it's not that big a deal. So the consequences of this fault are not all that severe. On the other hand, if I have lost a great many light bulbs, like all of the light bulbs in one of the space station nodes and the entire thing is dark, this is a rather more consequential fault. And so it may indicate that there's something wrong with the power system and that I've lost more than just light bulbs, and I've got to do something about it. So that's part of the difference between merely detecting a fault and doing this consequence assessment. And we'll talk some more about this in a little bit. So those are our four major mission operations functions. And so, like we said, if we think about the places that we want to go that are far from Earth, more than a few light seconds or light milliseconds delay, if we're going to the moon, perhaps 1.2 light seconds, 1.5 light seconds is not that bad, although it does become difficult when you're doing certain things. But certainly by the time we're going to Mars, we cannot imagine operating a human-rated spacecraft the way that we do operate the International Space Station. So we're going to have to do something different. And this is our motivation for AI. As we think about making the crew more autonomous using AI, this is asking, what's the right balance of responsibility between the crew and the ground? What's the right balance of responsibility between the crew and the vehicle? How is it that we're going to make all of this happen? And hopefully you'll see that AI is at least one of the ways that we need to think about how to solve that set of problems. All right. So we're a little bit behind schedule, but not doing too badly. Okay, so the next part of the talk is about technologies. So we'll just get right into it. So the first set of technologies we'll talk about is planning and scheduling. There's a relationship between these that we'll get into. There's much more to say about this. And if people have deeper questions, please feel free to ask later. So the purpose of planning and scheduling, I need to build a plan by choosing a set of activities that achieve goals. And I need to schedule these activities that I have chosen by ordering them and possibly choosing when they start in order to ensure that I don't violate any of their constraints. So let's talk about what some of these constraints look like. So I have a couple of these listed here in the middle of the slide. So one possible type of constraint that I may have is an absolute time constraint. So I may need to take a picture of some astronomical object or a target or a location on the Earth between 10 o'clock and 10:30 a.m. local time, so relative to the sun. So why would that constraint exist? This is a constraint that may arise because if I take the picture too early, then the image will be too dark. And if I take the picture too late, then the sun will be directly overhead, and the image quality will be no good because it's blown out, right? A similar constraint may be a relative separation constraint between two activities. So I may be told, you can't take the image less than 5 minutes after you have finished turning or rotating the spacecraft or pointing the spacecraft. So the reason for this may be that the spacecraft is vibrating and the attitude control system hasn't settled it down yet. And so if you take the picture too early, it'll be blurry. Okay, so that makes sense. We have a variety of different types of resource constraints that we may need to think about. One of them is some sort of consumable or replenishable resource like battery energy. So I may say, I may have a constraint that says I need to preserve battery state of charge. I need battery state of charge to stay above 65% because I don't want to deeply discharge the battery and damage it. I may have resource constraints that say that I can't do two things at the same time. For instance, I can't use two instruments at the same time because they interfere with each other. Either they generate too much power, or they have electromagnetic interference, any one of a number of different possibilities. So these constraints are scheduling constraints. These are things that tell me that I may need to order activities. But these planning constraints to achieve goals, these are a little different. So when I think about planning as opposed to scheduling, I'm thinking in terms of activity effects that are going to satisfy my goals, and also possibly establish the conditions that I need in order to execute other activities. So for instance, I may have a perspective on taking pictures that the power must be turned on in an instrument before I take an image, because otherwise, well, I can't take the image at all. I won't get the image. The other thing I may think about is the effects of taking a picture. I may get the image that I want, this picture that I have to take between 10 and 10:30, but I may use up available memory, 10 megabytes of memory, by taking that picture. So again, lots to talk about with planning and scheduling. This is sort of the big picture, the kinds of things that a planner and scheduler needs to do. Okay, so plan execution or task execution, and here we're going to really focus on the electronic command interface task execution as opposed to astronauts performing the activities in their plan. So the purpose of this is to carry out your plan using some kind of execution strategy. One of the execution strategies that we often think about is continuous control. I'm not going to talk too much about that in this talk. We're going to talk mostly about discrete control. And the perspective that's useful here is that if I have a plan which really is perform a task, then perform another task, then perform another task, without checking any conditions, without seeing whether the previous task was successful or not, without seeing if anything caused me to want to abandon a task, this is a very brittle and fragile plan. It's very simple to execute, but it doesn't have a lot of robustness to it. But if we can represent a plan to execute more like a program and include conditional evaluation in branches, loops in order to recover from transient failures, condition checks in order to ensure that I don't do things when conditions aren't right, now I have to be much more sophisticated in how I actually execute this plan. And this is the kind of AI-based technology that we're thinking about when we talk about task execution. And so I have a list of the kinds of checks that we can put into plans in order to enable this sort of thing. We talked about start times and end times. And then we can establish various conditions that we may wish to check. If there's a big bright object in my field of view, don't point the star tracker at it, because otherwise I'll either confuse my spacecraft or break the star tracker. All right. So now let's talk a little more about fault management. So as we said, we want to know whether a fault has occurred. We want to know what faults have taken place if a fault has occurred. And we want to assess any consequences, assessing remaining capability of the system after a fault has occurred. So one of the things that often comes up when we talk about fault management is the distinction between determining that I have a fault versus whether there's an anomaly or some sort of off nominal that isn't necessarily a fault. And an example I like to use here is that I'm riding my bicycle, or perhaps my unicycle, if there are any unicycle madness people out there. And I'm accustomed to a certain feel to the uni and maybe the road noise, but it's not the same as it usually is. So this is the anomaly. This is the off nominal. But it isn't clear to me immediately upon experiencing this anomaly whether or not it's just the condition of the road or whether I have a flat. So this is the kind of thing that we talk about, the difference between off nominal and faults. Anomalies and faults are related to each other, but they're not quite the same. Okay, so we discussed detecting whether a fault occurred. And the other thing that often comes up when we have faults is that we don't just get single faults. Faults don't come in single spies, but they often come in great battalions. And so when this happens, there's usually a root cause, a single explanation for all the faults that I have seen. And so this is what we mean when we talk about fault isolation. So fault isolation is the attempt to figure out what the root cause is. So if I've lost every single light bulb in my habitat or in my spacecraft, it's much more likely that the power system has suffered some kind of failure than that every single light has simultaneously burned out. It's not impossible, but that's the kind of thing that we do when we try and isolate faults. It's not always possible to isolate faults. We may not have quite enough sensors on our spacecraft in order to do that. And so if there's any ambiguity left, that makes consequence assessment a little bit more difficult, and otherwise just makes our lives more difficult operationally speaking. So the last thing, we talked about consequence assessment. And one of the things that we often think about, especially in human spaceflight with respect to consequence assessment, is whether I have lost capability or whether I have lost redundancy. And so let's use cameras as an example. So if I have a spacecraft with two cameras on them, one of them is a visible camera and one is a dual visible IR camera. Well, if I lose my IR camera, then I have lost the capability of taking infrared images. But I have not lost all capability to take visual images because I have a second camera. So I've lost redundancy in my ability to take pictures, but I've lost capability for IR. In human spaceflight, sometimes insufficient available redundancy is reason to either abandon a mission or abandon a mission objective. So it's useful for us to distinguish between those two things. And so that's an interesting element of consequence assessment and fault management. Okay, so that covers our core AI technologies. And I said that there were some associated technologies, and I've listed those here. So we'll talk about these. So because we're talking about human spaceflight, often what we're going to do is we're going to build AI in order to help our astronauts or possibly flight controllers. And when we do that, we have to talk human interfaces, which means that we have to talk human factors, user experience, user interface design, and all of those very important issues, and figure out how to integrate our AI successfully and make it usable by people. Mostly, when we talk about robotic spacecraft, we're talking about the other side, which is integration with lower level software. Sometimes we call this flight software. If we're talking about robots, this would be your lower level robotic software. And so the sort of opposite integration challenge that we face is how to put all of our AI together and integrate it not only with each other, but with these lower level software interfaces. Some AI technologies are very heavyweight. They're very computationally intensive. They're very memory intensive. And so it's important to think about the computing platform that we have at our disposal. Many space-based computers are very impoverished compared to what's on your desktop or what's even in your pocket. But there is some high-performance computing, high-performance space-based computing that is starting to become available. And so we want to keep tabs on that and figure out what we can use that's in space in order to make our AI a little bit easier to use. And last but not least, we'll talk about machine learning. So when we talk about machine learning, the first thing that we need to do is distinguish between the use of a learned classifier of some kind in space, but not doing learning in space, versus actually performing learning in space with data that the vehicle has at its disposal. And so there are some challenges with both of these, but they're not quite the same. So when we talk about a learned classifier, we can compute all kinds of useful metrics on our learned classifier. We can look at its training error. We can look at its validation error. The validation error can be computed in a variety of different ways, but that's on the data sets that we have been training it on. What about all the stuff that we've never seen? How confident are we that this thing is safe? How confident are we that it's going to do what we want it to do and that it's not going to do something else? So this is the verification and validation challenge of learned classifiers. The AI world is starting to figure out some ways to deal with this, and it's very interesting and exciting work, but it is by no means a solved problem. And then the separate challenge is learning on board. And never mind the computational expense of learning on board, both in terms of memory and CPU. There's the question of how do I curate my data sets? What am I learning? How do I know that this thing that looks like it's a bad example of whatever classifier I want to build, how do I know that? Where does that information come from? And if I cannot figure out how to solve these challenges, then it's going to be very difficult to convince anyone that you're actually going to do learning on board. So at least for the time being, my personal assessment for learning on board is probably not yet for human spaceflight, for all those reasons. All right. So that's the end of that, and I'm not quite sure how to go to the next slide. There we go. There we go. Okay, and so we've sort of talked through several of these points. That these are all challenges for AI. I'll touch on them very briefly, and then we'll get into the good stuff, and then get to some Q&A. So AI components typically haven't been developed with the idea that they are interfaced with each other ever. There are some systems that have been developed that attack this challenge, but it's by no means a solved problem. So system integration is a big deal. We touched on the human machine integration piece of the story already. And we hit some of the best practices and resource constraints of space-based computing. So these are all things that are still very much works in progress for using AI in space and human spaceflight in particular. Okay, so for about the next maybe 10 minutes, maybe a little bit less, the last thing that I will do is I'll talk about a couple of things that NASA has been doing in order to develop and test various types of AI. And I apologize in advance. We do love our acronyms at NASA, but I'll translate as best I can. And we'll just go ahead and get right into it. So the first of these that I'll talk about is a demonstration that we did in 2014. This is called the AMO TOCA SSC experiment. The purpose of this was to evaluate astronauts' ability to autonomously manage spacecraft systems. We did this on board the ISS. We mostly were looking in this project at using planning, monitoring, and fault management. And we did build some user interfaces because we had crew using the tool. So what is a TOCA, I hear you ask? So if you look at the middle picture on the right here, you see that there is an astronaut who is floating. Yes, this was taken on board the ISS. The astronaut is using an iPad to do something. And there's a little silver box that he's floating over. That is called the Total Organic Carbon Analyzer, or TOCA. The TOCA's purpose is to analyze the crew's potable water supply on board the ISS. It's one of a couple of different water quality monitors that we have on board the ISS. Water quality samples are taken a couple of times a week. There are a variety of maintenance activities that need to be performed at various different times during the month and over the year. And today, all of that activity is scheduled by a person on the ground. And the crew basically, puts the water sample in and more or less, goes about their business. And what we wanted to do is see if the crew could schedule all those activities on their own without the assistance of mission control. Make sure that when a water sample was done, that the hardware was behaving properly, also without the assistance of mission control. And so that's what we did. You can see there's a scheduling interface on the bottom here. This is actually what we flew for the crew. This was connected to a very simple automated scheduler that generated the sample, the complete schedule of activities for the crew to do. We built a separate interface that helped them understand if the device malfunctioned or not, and gave them words to respond in the event that it did. In addition to a fault management system, we built an anomaly detection system. You can see the sort of engineer's output of the anomaly detection system on the top there. And it should be the work of a moment to say, well, geez, is that a good water quality run or a bad one? I don't know. There's some points above that red line. And so we learned a great deal from this. We were 7 months on orbit, and it was a great experience. And getting that picture back was really exciting. We did the same thing for what are called the SSCs, which are the crew's personal laptop network. You can see one of those laptops in the left of that image. This was a somewhat simpler job, and unfortunately, the crew didn't really use that function, so we didn't learn as much from that as we would like. But still, this was a great experiment, and we learned a great deal. The next crew autonomy experiment I'll talk about is called AMO Express. It was another experiment to evaluate astronauts' ability to manage space systems. This was primarily focused on plan execution and the human interface component. And in order to explain this one, if we look at the picture on the bottom here, this is a picture of what's called an express rack. The International Space Station has a number of these express racks. These things are designed to make it very easy for scientists to build various types of physical and biological payloads. The payloads fit into the drawers. You can see there's a couple of drawers on the lower right-hand side of the picture there. And it makes for a very convenient form factor for experiment development. And then the purpose of the rack is to provide power, communication, computing services. The racks have smoke detectors built in to make sure that if the experiment lets the smoke out, that is well known and well understood, because fire in space is a very bad idea if you don't light it inside a little enclosed cabinet. But now someone has to manage this rack. So we learned that it takes between 30 and 45 minutes for 3 flight controllers 2 of them in Marshall Space Flight Center in Huntsville, Alabama, and one of them in Texas at Johnson Space Center to power on and configure an express rack that has been powered off. So the first thing that we did was develop a piece of automation that that was able to perform that entire function at the push of a button. And we tested that by having a flight controller do that job. And the next thing that we did was had the crew do it. And the interface that the crew used in order to do that task is what you see in the top right there. And so the interface has step-by-step procedure for actually turning the rack on and configuring it. There's live data that's coming from the rack and the automation telling the crew where in the process they are, whether everything is going right, and whether everything is not going right. So this too was a great experiment. We learned a great deal. In fact, we learned so much that we're doing it again. Meaning we learned that we didn't do it quite right the first time. So we're on the cusp of being able to do this again. Okay, switching gears here for a little bit. The next thing I'll talk about is what's called the T2 augmented reality demonstration. Augmented reality isn't exactly AI, but it's really cool. So it gets honorary AI status as far as this talk is concerned. So the purpose of this is to evaluate the use of augmented reality in performing inspection and maintenance procedures. And the procedure that we have in mind here is that the crew periodically have to inspect their exercise equipment to make sure that it's in alignment and that everything is working right, and possibly perform preventive maintenance. But there are no electronic command interfaces in order to do this inspection. It's very hands-on, it's very manual. And if the crew's hands are busy, then they can't be reading a procedure and figuring out what it is that they're supposed to do next. And if they run into trouble, then they have to call ground for help. And so the question is, does augmented reality basically make this job easier or harder for the crew to do it? You can see on the top right, this is through the Microsoft HoloLens view of the application that we built. It has these sort of animations that are telling the crew you're supposed to wiggle this part of the T2 this way. And on the bottom, you see an astronaut wearing the HoloLens and using the gestures in order to operate the HoloLens application. This is happening on board ISS right now. And we're getting a lot of great insight into how these apps need to be built, how the HoloLens works, whether it works right, or whether it needs some improvements. All right, so switching gears a bit more, now we're going to focus on fault management for the next couple of slides here. So we developed a technology called Advanced Caution and Warning, or ACAWS, and the purpose of this is to both do this fault detection and fault isolation and loss of capability and loss of redundancy calculation, and then present this information either to flight controllers, like you see on the top right, or flight controllers on the bottom right, or astronauts on the top right. And our original hope was that we could actually get this into Orion, which is the spacecraft that we talked about at the very beginning of the talk. And unfortunately, we were not able to do that. So I'm going to, in the interest of time, I'm going to skip to the next piece here, which is to set the stage for some more stuff. In addition to looking at how we would present the information to flight controllers, one of the other problems that we had to solve here was how to actually get this integrated with flight software. So if you imagine we have this fault detection engine, and there are some diagrams on the right that I'll explain later if anybody is interested. These are the things that are actually computing things like loss of capability and loss of redundancy. In addition to potentially presenting this to people, we have to figure out how to get this to run on an embedded processor that runs a real-time operating system, and to integrate it with the command and telemetry data stream that is presented by the flight software. So we were able to do that successfully, and we were able to show that we could actually run a fault management system that was scaled to roughly 1/3 of the size that we expect the Orion vehicle to be, which is pretty good. It needs to grow, but that was very exciting. And this work set the stage for the very last thing that I'll talk about, which is how to do planning, plan execution, and fault management, all integrated in flight software, in order to operate the gateway. So you'll remember at the very beginning of the talk, we talked about the gateway, which is this human outpost that will be in lunar orbit. So in addition to potentially reducing workload for the crew, the other thing that's important to know about the gateway is that it might be unoccupied for a long time. And we don't want flight controllers sitting there twiddling their thumbs very fast operating this thing. So the question is, how much can we make the gateway basically take care of itself? And so in order to do that, we need to integrate these three functions, and we need to have them working together as part of the flight software in order to keep the gateway operational while the crew's not present, and reduce flight controller workload, and also make it easy when the crew is present. So that is pretty much the end of my planned remarks. I am going to, in the interest of time, to make sure that we have plenty of time for questions, I am going to put the bibliography up here as a way of pointing out that this was the work of a great and wonderful team of people at 3 NASA centers, NASA Ames Research Center, which is where I work, NASA Johnson Space Center, and Marshall Space Flight Center in Huntsville, Alabama. I will drop a link to this first paper into the chat for people to take a look at. That paper has references to all the rest of these, and so people can certainly, feel free to take a look at it, send me questions afterwards if you want to know some more. And with that, I will stop sharing and we can go to the Q&A.
Great, thank you, Jeremy. And also, we will be sending out the link in our follow-up email too, so don't worry if you don't catch it in the chat. So Jeremy, you talked about classifiers. Could you please be more specific about the inputs and outputs? For example, what input features or data are you trying to classify, and the classes that you hope to categorize?
Sure. So we can actually, so the nice thing about classifiers is that you can classify pretty much anything. You can take more or less any piece of data as input, and you can, classify it any way you like. I'll give a couple of examples of things that we have actually deployed in the control center, and then the one example that we flew on board the ISS. So one thing that actually it's a piece of software that uses a classifier that's in the control center today. It's actually looking at the ISS control moment gyros, which are the things that basically help the ISS stay stabilized. And they're looking for specific signatures of degradation. So they're looking at things like rotation rates, rotation directions, currents, and other such things. And they're essentially, in fact, this is more of an anomaly detector and a clustering technique than a classifier. But essentially what you're looking for is the thing doing what it normally does? And if it's not doing what it normally does, then somebody's got a problem, and a flight controller is going to go take a closer look. So that's a technology that's been running in the ISS Control Center for, I think, at least the last 15 years. Is that right? 15? Maybe it's more like 10. So that's one. We use the same technology that was used to build that application in order to build the water quality analyzer anomaly detection system. That was looking at the liquid part of the water quality system. So the way that the water quality system works is that you put a water sample into it. The water sample is moved through the system and gasified, and then the gases are interrogated to look for both signatures of organic carbon and inorganic carbon as proxies for things that are growing in the water that are not supposed to be there. And so now we're looking at things like mostly pressures and temperatures and flow rates.
Great, thank you. If there's a possibility to cast a multi-class classification into multiple binary classification problems, which would be preferred?
Ooh, that's a great question. The short answer is I have no idea. I think that it would depend a lot on the application. The kinds of things that we would be concerned about are classification accuracy, first of all. How well are we doing both training and test and validation? Memory and CPU performance would be very important for us to look at if we were flying it in, let's say, the non-shirt sleeve environment. So the experiments that I described, the Toka SSE experiment, we were super lucky, and we actually were running in the shirt sleeve environment. So we got to run on the laptop computer network. So that was great. The AMO Express experiment that I described, that was a little bit more tricky. The automation that actually powered up and configured the racks is running on the same computers that the flight software of ISS is running on. The user interface is running on a laptop computer, and then there's a bridge that basically gets all the data out of the flight processors and gets it to the user interface so the crew sees what they see. And so depending on where the application needs to be run, you may be less resource constrained, but even the crew's laptop computer networks are pretty resource constrained, and they're managed pretty carefully.
Thank you. I'm going to one of our pre-submitted questions. How do you perform functional verification and validation on neural network systems that are often complex black boxes in nature when you can't anticipate every possible circumstance?
Yeah, this is a great question. So this is an area that I do not know as much about as I would like, but it's very interesting for obvious reasons. I would refer the questioner to DARPA's Explainable AI program, because I think that program actually had a whole bunch of research on questions exactly like this. But a technique that I recently encountered is what's called, let's see, what's it called? Adversarial robustness is the name of the technique. So when I train my classifier, I have a set of training examples. And I can use these things either as training examples to build my classifiers or as part of my test and verification set. What I want in adversarial robustness is I want to look at the classifier output, and I want to see if I can construct an input that misclassifies. This is a fake input, a synthesized input. I want to synthesize an input that is quote unquote misclassified a minimum distance away from one of my training inputs. So if you like, the decision boundary between two wrong classes is now very close to each other, right? So you can imagine that if I'm building classifiers, I want those distances to be as far apart as I possibly can. And so that's one technique, and it's not perfect, right? It's got its deficiencies, but that's one kind of thing that you can do in order to ask yourself, of all the classifiers that I could choose from, that I could produce with a given set of training data, I want ones where this robustness threshold is very, very large. So that's one technique. Another technique that you want to concern yourself with is, you can fuzz these things with noise. We're concerned about their susceptibility to radiation. So, could I put these things in a beam, for instance, and can I get wrong answers out of them because I stick them in a beam and subject them to radiation, heat, shock, vibe, it's all the same. And so those are the classes of things that we would want to look at when we test our machine learned classifiers.
Great, thank you. How would the systems be updated while the spacecraft is so remote? What kind of hurdles are most hard to overcome?
This is a problem that actually applies to any spacecraft software. Every single spacecraft has methods that you can use in order to do a flight software update. And it is exactly as terrifying as it sounds. The system needs to be designed for you to basically transmit a brand new flight software load to the computer, and then you have to shut the computer off, and then you have to turn it on again, and you have to use the new software and not the old software. It's a very, very scary thing to have to do. The AI part is no different.
Great, thank you. Our next question, how do you see future general purpose AI robots assisting with Earth orbit, the moon, and Mars exploration, construction, and habitation?
Oh, this is a great question. I should have had these queued up. Let me get a couple of things queued up here for people to look at in the chat. So there is actually quite a long history of robots that people have tried to make useful for spaceflight. The first one I'll talk about very briefly here is called Astrobee. So Astrobee is it's a small cube-shaped robot. It's maybe about, I don't know, it's probably about this big. And the Astrobees are designed to be free flyer robots so that they can fly around inside the International Space Station. And the purpose of the Astrobee project and various projects that use it is to do exactly that, to figure out how to develop robotic assistants that can help the crew do various tasks. And I will go ahead and drop a link to Astrobee in the chat. In fact, I think that a relatively recent Harvey Mudd grad served as an intern working on Astrobee not very long ago. So that's one. And I think it's fair to say that these kinds of robot helpers are definitely a work in progress. Robot navigation is a very, very difficult challenge. One of the problems I think that we have inside the station is that the environment is relatively volatile. Things are being moved around all the time. There are these giant cargo bags that are hanging off the walls. The internal environment is very complex. There are tons and tons of YouTube videos of astronaut fly-throughs of the International Space Station. To get an idea of just how complex it is, then you can watch those YouTube videos and you can see how interesting it is. Lighting is a big challenge as well. And so just being able to get around is difficult, let alone actually be useful and do things that are helpful. So there's still a long way to go, but the fact that the Astrobees are up there serving as experiment platforms is a great step in figuring out what we can and can't do with them. So with respect to things like construction, there's another project that I'll drop a link into the chat here called Armadas. Armadas is a very, very intriguing project because of a couple of different things. So the way Armadas describes itself, it's essentially not a team of robots, it's actually a smart material. And the reason why it's a smart material is a combination of the structural members that are used to build very complex structures. So they're very similar, they're sort of geometric shapes. They're made of a lightweight material, but when you assemble them properly, you can build very, very strong, very, very lightweight structures. But in order to do that, you need a team of robots that know how to move them around and put them in the right place. And the team of robots that's being developed by the Armadas project is fully decentralized. So there is no centralized controller. The robots basically are capable of building these structures in a totally decentralized way. So it's a really very interesting project, very forward-looking. And the hypothesis is not only can you have these very lightweight materials that are assembled by a totally decentralized team of robots, but that you can build these structural members out of things that you find on the lunar surface, like lunar regolith, which is a bit of a stretch, shall we say. So, this is science fiction stuff, but it's very exciting and it's really interesting. And the project is doing some really great work.
Thank you. What is the process like to approve new AI applications in future missions? And do you have any examples of recent missions that allowed an unproven or risky autonomous system?
The answer to the second question is absolutely no. That's pretty much verboten. We don't do that. And you can sort of see why, right? You're putting a lot of time and energy into building this spacecraft. You're not going to put anything on it that you don't trust or believe in. And so when we talk about the process of deciding whether something is safe to use or not, again, it's much like the process of deciding that any piece of software that's on your vehicle is safe to use. You have to know what it's for. You have to have a set of requirements. You have to have a set of test objectives that you need to satisfy in order to decide whether or not the thing is working the way that it's supposed to. And if it doesn't work, then it doesn't fly. It's that simple. I'll tout possibly the most exciting achievement in AI that I think we've seen to date. So many of you may know about the Mars Perseverance rover, which has been on the planet for just about a year now. So both Perseverance and Perseverance's predecessor, Curiosity, used some very advanced, not exactly AI, but they used some control systems technology in order to dramatically reduce or dramatically increase the precision of landing compared to any previous generation reentry system. So this is more like active continuous controls than anything else. But Perseverance is going to have an automated scheduler on it. No previous Mars rover mission has had an automated scheduler that runs on board. There have been some technology demonstrations, but this will be the first time that a Mars rover has that sort of software on it. So that's a pretty amazing achievement. And all props to JPL and the Perseverance flight software team for that.
That's awesome. Thank you. I guess for our final question, or I guess inquiry, you received the NASA Silver Snoopy Award, which is an extremely high honor. Can you tell us a little bit about that, like what that is?
The NASA Silver Snoopy, yeah. So I should have done my homework on the origins of this too, but I'll drop another link in the chat here. So in the Apollo era, and possibly even before, NASA wanted a mascot to represent safety, astronaut safety, mission safety. And I cannot remember whose idea it was to use Snoopy as the mascot, but they actually went to Charles Schultz and they said, we would like permission to use Snoopy internally as the sort of safety mascot, and Schultz actually gave his permission. And so all throughout the human spaceflight part of NASA, you'll see Snoopy as sort of the safety representative. So the Silver Snoopy Award is referred to as the astronaut's personal award. You can get exactly one of them in your career ever, if you get one at all. And the astronaut corps makes the decisions about whether those people who are nominated deserve that award. I cannot adequately explain why they decided I deserved one. And as an example of other people who've received this award, when I found out that I got it, I said, well, so who else gets this? I have no idea. Well, so one of the other people who received this award was the person who designed all of the mechanisms that are used by crew who go out, astronauts who go outside spacecraft on EVA in order to secure themselves and to orient themselves in order to basically stay secure at their work sites while they're doing their work. So I'm sort of embarrassed to be mentioned in the same breath as a person like that, but there you have it. No, so this is an award that gets given to people who make great contributions to human spaceflight, and it was a great honor, and I'm super happy that I got one, and it's just a marvelous thing. So there you go.
Well, thank you and congratulations on the award. I want to thank Jeremy for joining us today and for sharing your knowledge and insights with us. Thank you to our audience for your questions and for attending this event. We will follow up within the next week with a recorded video and any presentation material. Keep an eye out for future Mud Talks. If you are interested in being a Mud Talk speaker, please contact us at alumni@hmc.edu. Future events can be found on our website by visiting alumni.hmc.edu. Thanks again for joining us tonight and have a great night, everyone. We'll see you next time.